back to the channel of ChemPacific. In this video, I'm going to discuss with you the crystal field theory from the chapter Coordination Chemistry. So if you are new to our channel, don't forget to subscribe our channel and press the bell icon. And also if you like our video, do press the like button. Now let's get started. In my last video, I discussed with you all the valence bond theory and also its limitation as well as the drawbacks. So in order to overcome them, a new theory has been postulated, that is the crystal field theory. So basically it is a hypothetical model in which two assumptions were made. The first assumption was that the ligand were considered as the point negative charge and the positive nucleus of the metal, they are considered as the point positive charge. Since there is introduction of the charge, therefore there must be electrostatic force of attraction as well as repulsion. Attraction between the positive and the negative charge and repulsion between two negative charges. Now, यहाँ पे नेगेटिव चार्ज तो आपको समझ में आ गया है कि लिगैंड है एंड मेटल है पॉजिटिव चार्ज एंड ऑल्सो the valence shell orbitals of metal, they are also electron cloud density, it means they are negative charge. In this case, the Deorbitals of metals are nothing but electron cloud density. And they create repulsion with the ligands, since ligands are considered as point negative charge. They create what? They create repulsion. So as because यहाँ पे दो चीज का information दिए गया है, the metal they considered as a point positive charge, rather the positive nucleus of the metal, and the ligands are considered to the point negative charge. Therefore, there are two forces. One is the electrostatic attraction between the positive nucleus of the metal and the negatively charged electrons of the ligand. And this ligand are also imagined as the point charges. ठीक है? And एक तो हो गया आपका attraction, दूसरा हो गया आपका electrostatic repulsion between the electrons in the valence shell and the ligand electrons. So in this case, the electrons in the valence shell are mostly the Deorbitals. So यहाँ पे it is very much clear to us that two types of electrostatic force of attraction there. One is the attraction and one is the repulsion. Always remember, in inorganic chemistry, the certain things which is very important for you to understand. The attraction results in stabilization. This is very important. And the repulsion results in destabilization. Okay? Obviously, एक complex formation होने के लिए what happens? The ligands they approach the metal and result in the formation of the complex. Now, formation of complex is a very stabilizing factor. That is why you must be knowing that in this case, the attraction is very much more as compared to the repulsion. That is why the formation of complex is taking place. Okay? The attraction is definitely more, very much more than the repulsion between the ligand and the Deorbitals of the metal. At the same time, some more informations are also important. Number one is that the negative charge in inorganic chemistry, it means stabilization. And if you are giving any negative charge to any crystal stabilization energy or anything like that, it means the negative charge indicates that it is stabilized and it is of low energy and they lie below the barycenter. Okay, and the positive charge is due to unstable, the one which is of higher energy. And it lies above the barycenter. Clear? So this information is very important for you. So I hope all these things are very much clear to you. Now let us understand the d orbitals. So as I already informed that the d orbitals and the ligands, they actually experience a repulsion due to each other. Now let us understand the d orbitals. And this repulsion also depends on the orientation of the d orbitals in space. So since it is d, it means it is 5 degenerate and is consisting of 5 degenerate orbitals. Out of this, 3 are in between the axis and 2 are along the axis. The orbitals dxy, dyz and dzx, they are the atomic orbitals which lie in between the axes. Okay, so in order to maintain the simplicity, I have taken the axis as वेरिएबल फैक्टर्स, मतलब कोई फिक्स्ड एक्सिस मैंने नहीं किया है, मैंने वेरिएबल किया है, ये फिक्स सबके लिए नहीं है ताकि ये बहुत सिंपल हो जाए आपको समझने में. तो यू कैन सी व्हेन द ऑर्बिटल इज dxy, then the orbital is lying between the x-axis and the y-axis. When the orbital is dyz, the orbital is lying between the y-axis and the z-axis. When the d orbital is dxz, it means the d orbital is lying in between the x-axis and the z-axis. It means whenever any ligand is going to approach in between the axis, when the approach of the ligand in between, then the orbitals, which are the orbitals? dxy, dyz and dxz. These orbitals, they experience maximum repulsion. They experience what? They experience maximum repulsion, and therefore they are going to be energetically high. तो एक लाइगेंड की अप्रोच कौन से डायरेक्शन में हो रहा है एंड उस डायरेक्शन में जो ऑर्बिटल का ओरिएंटेशन होता है, obviously that d orbital is going to experience more and more repulsion and that is going to be higher in energy. Now let's talk about the last two orbitals, that is the dz square orbitals and the dx square minus y square orbitals. ओके, सो यहाँ पे एक थोड़ा सा मिस्टेक है, आई एम सॉरी. दिस इज dx square minus y square orbitals. Let me correct this as well. dx square minus y square orbitals. Now let us discuss about these two orbitals. Then this is the dz square orbitals and the x square minus y square. This is the two orbitals which actually lie along the axis. The dx square minus y square orbital lie along the x-axis and the y-axis, and the dz square orbitals mostly lie along the z-axis. Now this dz square orbital has very interesting things to be known. Now let us understand the nature of the dz square orbital even better. It is very important for us to understand the nature of the dz square orbital. Now, this is a representation of the dz square orbital, which is considered as the linear combination of two orbitals and their dz square minus x square and dz square minus y square. That's what I have done in this diagram. This is the linear combination of dz square minus x square and dz square minus y square, and that results in the formation of dz square. You can see that this dz square minus x square is lying along the z-axis and x-axis, and this is lying along the z-axis and y-axis. Now, these two orbitals, dz square minus x square and dz square minus y square, they have no independent existence, but they are thought to be combining, and it is thought that the linear combination of these two orbitals results in the formation of dz square. That is why this dz square is having the average properties of these two. It means you can see that both these orbitals, dz square minus x square as well as dz square minus y square, both these orbitals, they have high electron density along the z-axis. That is why this dz square orbitals is having a large fraction of electron density concentrated along the z-axis. So इसका मतलब ये है that dz square का electron density along the z-axis is extremely high. Clear? But at the same time, you can see there is a torus. There is a torus. ठीक है, इसे कभी भी आप इग्नोर नहीं कर सकते हो. ठीक है. Now you see that ये जो orbital है, इसका एक segment, एक component is lying along the x-axis, और ये जो है, it is lying along the y-axis. That is why you can say that the resultant जो formation dz square का हो रहा है, this is having a torus of electron density in the xy plane. ठीक है, and this xy segment is very important. You cannot completely ignore this torus of electron density which is in the xy plane. It means अगर कोई ligand का approach along the xy plane हो रहा है, then definitely to some extent the energy of the dz square will definitely get affected and will surely to some extent will increase. Clear? So this is very important. Let me recapitulate once again. So basically dz square is a linear combination of d z square minus x square and dz square minus y square. And even though these two orbitals, they have no independent existence, but dz square can be thought of having the average properties of this both. And since both of them are having high electron density along the z-axis, therefore dz square also have a large fraction of its electron density concentrated along the same axis. At the same time, since both of these orbitals, they have one of the component of the wave function of electron density along the x-axis, while the other is having the one of the component of the wave function of electron density at the y-axis. Therefore, the resultant जो dz square इन दोनों से बन गया, इन दोनों का linear combination बना है, it has a torus of electron density in its xy plane. इसका मतलब ये है, अगर कोई ligand का approach along the xy plane होता है, then dz square का energy definitely to some extent affected definitely होगा और ये increase हो जाएगा. I hope this is clear to all of you. Clear? Now let's proceed. Now हम splitting in a linear field करने वाले हैं. Now see students, linear field splitting एकदम simple से हम start करेंगे. यहाँ से हम वही मैं बोल रहे थे कि एक ligand का approach जिस direction में होगा, उस direction में जो orbital रहते हैं, वही orbital maximum repulsion experience करेंगे. For example, the p orbital is triply degenerate and it is consisting of three px, py and pz, three degenerate orbitals. One is along the x-axis, the other along the y-axis, and the one pz is along the z-axis. And that is why if the approach of the ligand is along the Z axis. Then what will happen? Then the orbital PZ, which is lying along the Z, is closest to this, and it is experiencing maximum repulsion. And as a result of which, its energy is going to increase. ठीक है, बाकी जो दो ऑर्बिटल है, they are 90 degree to the approach of the ligand and they are experiencing least energy. इसीलिए pz का एनर्जी सबसे ज्यादा हो जाता है and px and py का एनर्जी कम हो जाता है. एंड ऑल्सो ये दोनों ऑर्बिटल पेरिसेंटर से जितना स्टेबिलाइज्ड हुआ है, ये उतना ही डिस्टेबिलाइज्ड हुआ है. क्लियर? नाउ लेट अस कंसीडर द d orbital. अगर मैं एक लीनियर फील्ड में ऐसे सोच रही हूँ that the approach of the ligand is, again if I am considering that the approach of the ligand is along the z axis, एकदम सिंपल से करेंगे तो आपका कंसेप्ट और क्लियर हो जाएंगे. The approach of the ligand is along the z axis, then what will happen? Then obviously, since this d orbital is consisting of 3 orbitals which are lying in between the axis, that is dxy, dxz and dyz. These are in between the axis, and the orbitals dz square and dx square minus y square, these two orbitals are along the axis. Now approach of the ligand is along the z axis. तो जो d orbital जिसका z axis में maximum इलेक्ट्रॉन क्लाउड डेंसिटी है, वो मैक्सिमम रिपल्शन एक्सपीरियंस करेंगे. तो नंबर 1 पोजीशन में क्या होगा? dz square, because we know that the electron cloud density of the dz square at the z orbital is maximum. So सबसे ज्यादा एक्सपीरियंस रिपल्शन एक्सपीरियंस करने वाले dz square. Now even though dxz and yz, they lie in between, dxz is lying in between the x and the z axis, and dyz is lying in between the y and the z axis. They are the second closest to the approach of the ligand. That is why इसका position हो जाएंगे second. And the last, which are dxy and dx square minus y square, जिनका कोई भी इलेक्ट्रॉन क्लाउड डेंसिटी वेव फंक्शन जो है वो कोई भी z एक्सिस के नजदीक में है ही नहीं, तो ये सबसे कम रिपल्शन एक्सपीरियंस करेंगे और ये काफी स्टेबलाइज्ड हो जाएंगे. सो अकॉर्डिंगली द मैक्सिमम रिपल्शन इज गोइंग टू बी एक्सपीरियंस्ड बाय द dz स्क्वायर. इसका एनर्जी सबसे ज्यादा हो गया. इसके बाद dxz and yz, एंड लास्ट which is dx square, x square minus y square and dxy, which have no electron cloud density in the z axis or not on the z axis and also in between the z axis. तो ये काफी दूर है और वो स्टेबिलाइज्ड हो जाते हैं. अच्छा, ये बैरिसेंटर के नीचे क्या जितना ये स्टेबिलाइज्ड हुआ है, ये 3 ऑर्बिटल बैरिसेंटर के ऊपर उतना ही डिस्टेबिलाइज्ड हुआ है. एंड दिस आई एम गोइंग टू एक्सप्लेन यू नाउ एज वेल. Now splitting of the d orbitals. Now this is the splitting of the d orbitals in an octahedral field. This is very important. Before I explain this, before I proceed with this, let me explain you certain important concept about this. Point number 1, ये splitting क्यों होता है? Why is this splitting happening? और ये होने के बाद क्या होता है? Point number 2, what I'm going to discuss with you is, what do you mean by the A, T, E, D orbitals? ये इसका मतलब, ये notations का मतलब क्या है? Point number 3, Jared subscript का मतलब क्या है? Point number 4, अगर मैं T2J लिख रही हूँ, what does this 2 indicate? ठीक है, ये सारे बहुत छोटी छोटी बात है, बहुत इंपॉर्टेंट है. एंड नेक्स्ट, ये जो साइन है पॉजिटिव और नेगेटिव, ये मैंने एक्सप्लेन किया है, इसका भी मतलब क्या है. तो दिस आर द वेरी माइन्यूट डिटेल्स एंड आई फील दैट द स्टूडेंट्स मस्ट अंडरस्टैंड दिस माइन्यूट डिटेल्स सो दैट जो हम एडवांस लेवल में आप लोगों को पढ़ाने वाले, सुपर एडवांस लेवल, तो आपको समझने में कोई प्रॉब्लम नहीं होगा. एंड द बेटर यू अंडरस्टैंड, द मोर यू स्कोर. ऑलवेज रिमेंबर दिस. सो स्प्लिटिंग क्यों होता है ये तो आपको समझ में आ गया है। क्या समझ में आ गया है? स्प्लिटिंग इसलिए होगा बिकॉज एक लिगैंड का अप्रोच जब होता है अलोंग द एक्सिस और इन बिटवीन द एक्सिस, तो उसके नजदीक में जो डी ऑर्बिटल होते हैं दैट एक्सपीरियंस मैक्सिमम रिपल्शन एंड हेंस इसका एनर्जी इंक्रीज हो जाते हैं और फिर बंद हो जाता है। स्प्लिटिंग क्यों होता है? इसलिए स्प्लिटिंग होता है ताकि वो कॉम्प्लेक्स स्टेबिलिटी अटेन करे। दिस इज वेरी इंपॉर्टेंट। So due to the splitting, the complex attains stability and it overcomes the repulsion caused due to the approach of the ligand. Definitely एक ligand एक मेटल है उसमें एक लिगैंड अप्रोच कर रहे हैं। जब अप्रोच हो रहा है रिपल्शन भी होता है, अट्रैक्शन भी होता है। अट्रैक्शन काफी ज्यादा होता है इसलिए कॉम्प्लेक्स फॉर्मेशन हो रहा है और जो रिपल्शन है उस रिपल्शन को जो एक्सपीरियंस डी ऑर्बिटल कर रहे हैं उसे ओवरकम करने के लिए स्प्लिटिंग होता है। मींस स्प्लिटिंग होने के बाद जो रीअरेंजमेंट होता है, स्प्लिटिंग होने के बाद जो रीअरेंजमेंट होता है उसके वजह से इट अटेन्स स्टेबिलिटी। ये समझना बहुत इंपॉर्टेंट है बिकॉज जब हम एंटीलर डिस्टॉर्शन करेंगे यहाँ पे जेड इन एंड जेड आउट जो है वो स्टूडेंट्स मैक्सिमम स्टूडेंट्स वहाँ पे समझने में गलती करते हैं। ठीक है, तो हमेशा याद रखो कि ये स्प्लिटिंग इसलिए होता है ताकि जो रिपल्शन वो एक्सपीरियंस कर रहे थे उसे वो ओवरकम कर सके और वो स्टेबिलिटी अटेन कर सके, इसीलिए ये रीअरेंजमेंट होता है। नाउ द नेक्स्ट A orbital A notation results in singly degenerate. T results in triply degenerate. मतलब अगर 3 same energy orbitals lie in the same energy, it results to the T, that is a triply degenerate. And when there are 2 orbitals of same energy, it is defined as E, which means doubly degenerate. Now this is Gerard. Now Gerard is mainly explained in 2 different ways. For example, अगर आप D orbital के बारे में कर रहे हो, so this is your d orbital and the signs are plus, minus, plus, minus. Clear? Now, आप कोई भी point, you take any point and you pass through the center and reach exactly opposite distance to the opposite direction and you must pass through the point. Say यहाँ पर भी आपका minus sign है, यहाँ पर भी there is no change in sign. And also you can take a point from here also. You must pass through the center and reach exactly the same distance in the opposite direction. And you see there is also no change in the sign. Plus plus ही रहते हैं. अगर there is no change in sign, when you take a point, you pass through the center and you reach exactly the same distance to the other side, then it is defined as Gerard symmetry. So you see, this must consist of a center. ठीक है? In the case of the octahedral geometry, what happens? Since the ligands are now considered to be the point negative charge, and that is why if you start from one ligand, ठीक है, you pass through the center and you reach exactly the same distance in the opposite direction. You find the same point negative charge, and this orbital is this octahedral geometry is therefore centrosymmetric. And it means it is possessing a centrosymmetry. And therefore, the Gerard subscript is used in the case of the octahedral field. Now, what does this 2 indicate? 2 means when it is antisymmetric. When it is antisymmetric, when the orbitals are antisymmetric with respect to the subsidiary axis or molecular plane. Or molecular plane. Then that is why this two subscript is used. I hope इसके हर एक minute details मैंने आप लोगों को explain किया है. Yeah, this one is remaining. Plus and minus sign. Obviously, when it is minus sign means it is stable and it has to be below the barycenter. And when it is plus sign, it is unstable and it is above the barycenter. So every single minute details मैंने आप लोगों को explain किया है. Now let's understand the d-orbital splitting in the octahedral field. Now यहाँ पे जो unit दिया है dq, so you must be knowing that 1 delta 0 is equal to 10 dq. Now एक octahedral field अगर आप देखते हो, this is your octahedral field. This octahedral field अभी तक complex formation नहीं हुआ है, लेकिन यहाँ पे आप जानते हो if this is the x and y axis, so it is consisting of this orbital. This is the x and y axis, so this is the orbital dx square minus y square, and this is, there is a presence of orbital along the z axis and this is dz square. So अभी तक ये metal है, अभी तक ligand का approach नहीं हुआ. अब ligand approach कर रहे हैं which is along the axis. As a result of which, now this is clearly this is visible to all of you that the approach of the ligand is closer to the two orbitals, that is the dz square and the dx square minus y square. So now due to the approach of this ligand, the orbitals which are along the axis, which are the dz square and dx square minus y square, these two orbitals, they experience maximum repulsion and इसका energy भी high हो जाता है. यहाँ पे एक दो orbital है, इसलिए E subscript is used, and the orbitals which are in between the axis, that is dxy, dyz and dxz, these three orbitals are in between the axis, and since there are three orbitals, so T subscript is T is used, and 2 indicates that these orbitals are antisymmetric with respect to the subsidiary axis or molecular plane, and G subscript is used because this is octahedral complex, and in this octahedral complex it is centrosymmetric and is possessing the center of symmetry. So I hope this is very much clear to all of you. Now the sign. So I already informed you, whenever it is going to be stable, it is denoted by the negative sign. This is minus 4 this, and whenever it is unstable, it is denoted by the positive sign. So it is plus. Clear to all of you? So जो negative sign है, देखो these orbitals are below the barycenter and ये orbitals positive sign है, they are above the barycenter. Now the next question arises, इसका जो energy level दिया है ना 0.4 delta 0, ठीक है, तो इसका मतलब क्या है और ये क्यों दिया है? देखो ये जो TTG orbitals है, it can accommodate maximum up to 6 electrons, ठीक है. So इसका क्या है? crystal field stabilization energy फिर क्या हो जाएगा? Number of electrons, that is 6 into the energy of T2G, that is minus 0.4 delta 0, which is equal to minus 2.4 delta 0. मतलब ये barycenter से exactly 2.4 delta 0 energy level नीचे है. ये जितना stabilized हुआ है ये तीन orbital, Eg का जो दो ऑर्बिटल है वो उतना ही डिस्टेबलाइज्ड होगा इन ऑर्डर टू मेंटेन द ओवरऑल एनर्जी ऑफ द कॉम्प्लेक्स। तो मतलब अगर इसका -2.4 एनर्जी नीचे हुआ है, मतलब रादर 2.4 एनर्जी नीचे हुआ है फ्रॉम द बैरिसेंटर, इसका भी 2.4 ऊपर होना चाहिए। कैसे है मैं दिखाती हूँ। इट कैन एकोमोडेट मैक्सिमम अप टू 4 इलेक्ट्रॉन्स। तो इसका CFSE कितना हो जाएंगे? नंबर ऑफ इलेक्ट्रॉन्स दैट इज 4 इनटू, यहाँ पे प्लस है साइन, 0.6 डेल्टा 0। देखो इसे तो साइंस कहते हैं, जो आप लॉजिकली सोचते हो साइंस तुरंत वो प्रूफ कर देते हैं। इसीलिए जो क्वेश्चन का आंसर आप लॉजिकली सोचोगे, अगर आप साइंस समझते हो, वो तुरंत सॉल्व हो जाएंगे। किसी को सारे क्वेश्चन सॉल्व करने के, ये कोई थियोरेटिकल पढ़ाई नहीं, ये साइंस है। साइंस का मतलब समझो, ठीक है। तो यही है, ये 3 ऑर्बिटल बैरिसेंटर से जितना स्टेबिलाइज्ड हुआ है, द स्टेबिलिटी इज डिफाइंड बाय द साइन नेगेटिव। कितना हुआ है? 2.4 डेल्टा 0। और फिर ये दोनों ऑर्बिटल बैरिसेंटर से उतना ही डिस्टेबलाइज्ड हुआ है, एंड द डिस्टेबिलिटी इज डिफाइंड बाय द प्लस साइन। ये -2.4 डेल्टा 0, ये है +2.4 डेल्टा 0। तो देखो हर एक चीज जो होता है साइंस में, हर एक चीज का एक्सप्लेनेशन 101% होता है। अगर नहीं होता तो वो बुक में कभी प्रिंटेड नहीं होता, ठीक है। तो ये साइंस को हमेशा रिस्पेक्ट करो और समझ के पढ़ाई करो। नाउ ये हमें समझ में आ गया। नेक्स्ट वी आर गोइंग टू मूव टू द स्प्लिटिंग ऑफ द टेट्राहेड्रल फील्ड। सो बेसिकली टेट्राहेड्रल फील्ड बनते कैसे है? अगर आप एक क्यूब लेते हो, उसका जो ऑल्टरनेट कॉर्नर्स है, ठीक है, ये पोजीशन 1 3 5 7, इसका ऑल्टरनेट कॉर्नर्स का जो लिगैंड है, अगर आप उसे रिमूव कर देते हो, इट रिजल्ट्स इन द फॉर्मेशन ऑफ टेट्राहेड्रल। Now in the tetrahedral field there is certain important point that has to be explained, and that is point number 1, tetrahedral में कोई भी center of symmetry नहीं है. It consists of no center of symmetry. Clear? That is why कोई भी Gerard या ungerous subscript, they are not used in the case of the tetrahedral complex. At the same time, जो हम CFSE के बारे में बात कर रहे थे, वहाँ पे आप देखेंगे the value of delta T is very much less than the value of delta 0. ये मैं ज़रूर आप लोगों को explain करूँगी, and that is why tetrahedral complexes, always remember, that is why tetrahedral complexes are always or mostly always high spin complexes. It means they cannot afford the pairing of the electrons. क्योंकि पेयरिंग करने के लिए CFSE का वैल्यू काफी स्ट्रॉन्ग होना चाहिए, ठीक है। So these things has to be kept in mind. लेकिन अभी जब टेट्राहेड्रल कॉम्प्लेक्स फॉर्मेशन हो रहा था, पहले एक मेटल था, अभी लिगैंड का अप्रोच। इन द केस ऑफ द टेट्राहेड्रल फील्ड, द अप्रोच ऑफ द लिगैंड is in between the axis. That is why the orbitals which are in between the axis, that is dxy, dyz and dzx, ये orbital are now closest to the approach of the ligand, and that is why ये orbitals का energy in this case अभी high हो जाएगा। क्लियर? ये ऑर्बिटल की एनर्जी अभी काफी हाई हो जाएगा। नाउ एट द सेम टाइम, सिंस द ऑर्बिटल्स dx² minus y² and dz² and now they're along the axis and they are experiencing very less repulsion, that is why they are stabilized and इसका एनर्जी लो हो जाएगा, ठीक है। At the same time, you must be understanding that the approach of the ligand are not straightforward. मतलब direct ligand और metal का straightforward नहीं हो रहा है. तो जैसे कि मैंने कहा एक कॉम्प्लेक्स फॉर्मेशन के लिए अट्रैक्शन होना बहुत ज़्यादा ज़रूरी है और अट्रैक्शन बहुत स्ट्रॉन्ग है। मैंने क्या कहा, एक कॉम्प्लेक्स फॉर्मेशन होने के लिए अट्रैक्शन होना बहुत ज़रूरी है। अट्रैक्शन काफ़ी स्ट्रॉन्गर होगा एज कम्पेयर टू द रिपल्शन, दैट इज वाई द फॉर्मेशन ऑफ द कॉम्प्लेक्शन इज टेकिंग प्लेस। दिस अट्रैक्शन टेक्स प्लेस बिटवीन द पॉजिटिव न्यूक्लियस ऑफ द मेटल एंड द लिगैंड, है ना। यहाँ पे अट्रैक्शन होता है बिटवीन द पॉजिटिव न्यूक्लियस ऑफ द मेटल एंड द लिगैंड। मतलब जितना नंबर ऑफ लिगैंड ज्यादा होगा उतना ज्यादा क्या होगा, अट्रैक्शन होगा, है ना। जितना ज्यादा नंबर ऑफ लिगैंड्स होगा उतना ही अट्रैक्शन होगा। इट मीन्स ऑक्टाहेड्रल में कितना लिगैंड था, ऑक्टाहेड्रल में 8 था एंड टेट्राहेड्रल में कितना हो गया, टेट्राहेड्रल में 4 है। एज अ रिजल्ट ऑफ विच द attraction, electric force of attraction decreases and delta T decreases by 2/3 amount. Since there are 4, in this case 2/3 amount of delta 0. Since there are 4 points charges as compared to the 6 point charges of the octahedron. Clear? At the same time, since I already informed that in this case, none of the metal ligand interaction in the tetrahedral complexes are straightforward. इसके वजह से attraction और कम हो जाता है और as a result of which the delta T, the crystal field stabilization, again decreases by 2/3 amount. Overall कितना हो गया? Overall आपने देखा that the tetrahedral 2/3 into 2/3 which was the 4/9 of octahedron, that is nearly half of the octahedron. क्लियर? ये सारी चीज आपको क्लियर हो गया। सो अभी इसे एक्सप्लेन कर देते हैं। नंबर 1, सिंस यहाँ पे जो अलोंग द एक्सिस थे कौन कौन थे, डी एक्स स्क्वायर माइनस वाई स्क्वायर एंड डी जेड स्क्वायर, दे वे अलोंग द एक्सिस एंड दे आर स्टेबिलाइज्ड, सो इसका एनर्जी कम हो जाएंगे। and the orbitals which were in between the axis dxy, dyz and dzx. Now they are in between the axis and they are experiencing more repulsion due to the approach of the ligand along the in-between axis, and therefore they are now energetically high. So that is why in this case you are using T2 as the high energy and E as the low energy. And in the similar way यहाँ पे जब ये नेगेटिव साइन हो जाएंगे, जब E होता है ये डिस्टेंस बिटवीन द बैरीसेंटर एंड द E ऑर्बिटल इज ऑलवेज 0.6, ठीक है। और सिंस इट इज बिलो द बैरीसेंटर यहाँ पे ये नेगेटिव हो जाएंगे और इसका चार्ज यहाँ पे पॉजिटिव हो जाएगा। एट द सेम टाइम वन मोर इम्पोर्टेंट इंफॉर्मेशन इज देयर, दैट इज यहाँ पे आपको क्या लिखना है, डेल्टा टी। तो स्टूडेंट्स यहाँ पे गलती करते हैं, यहाँ पे भी डेल्टा 0 बिठा देते हैं, नहीं करना है क्योंकि जब हम स्पिनर्स करेंगे वहाँ पे कैलकुलेशन में आपको गलत होगा। तो आपको इसका CFSE निकालना है, अल्टीमेटली CFSE का जो वैल्यू निकाल लेंगे वो डेल्टा टी में आएंगे, देन यू हैव टू कन्वर्ट इट इनटू डेल्टा 0 बाय मल्टीप्लाइंग विथ 4/9 ऑफ डेल्टा 0। एंड ऑल्सो वन मोर थिंग, यहाँ पे कोई जेरड सब्सक्रिप्ट इज नॉट यूज्ड बिकॉज tetrahedrals are non-centrosymmetric. Clear? Now the last but not the least is the crystal field splitting of the cubic environment. So basically cube, वही मैंने आप लोगों को कहा, एक क्यूब जो है जो टेट्राहेड्रल था तो वहां पे जब आपके सारे कॉर्नर्स में आप लिगैंड्स आ जाते हैं, it results in the formation of the cube. और अगर आप देखेंगे that cube is centrosymmetric, that is why in this case this is Gerard in nature. That is why in this case the Gerard subscript is used. And this cube is consisting of how many ligands? So cube is consisting of 8 ligands and tetrahedral complexes are consisting of 4 ligands. तो यहाँ पे क्यूब में अट्रैक्शन डबल हो जाते हैं, therefore the delta cube C is equal to 2 of delta T. So therefore हमें क्या मिला ओवरऑल, tetrahedral crystal stabilization is 4 by 9 of octahedral stabilization and is equal to half of the CFAC of the cube. Clear, students? So this is very important. So let's end the video over here. I hope you like it. If you like it, do press the like button. It actually encourages us a lot. So thank you for watching our video.